Okay.
Well, thank you for letting us know.
And we don't need that, right?
Do you want it in? Do you want it in presentation mode?
And I should meet my here, so it's not-
But then can I still do this? It's too late. I should have.
It's fine. Okay. Yeah. Okay, let's leave my phone beside you and hope that it works the whole time. Okay, let me know when you're ready, Howie.
Yeah, we're all set up here. I'm also going to keep an eye on the chat, so if any questions come up via the chat session, I might interrupt to
Sure.
ask those.
Yeah. So thank you all for coming. So today we're happy to have Bruno Nachtergaele from UC Davis, who's going to talk about the stability of the bulk gap for quantum lattice systems. So thank you for coming.
Thank you very much, Agnes, and everybody for having me today and give a talk in this mathematical physics seminar I'm familiar with, but for the first time in person. So I will give some context, but then sort of the main result I'm going to talk about and present here is joint work with Robert Sims from the University of Arizona and Amanda Young, who is currently still a postdoc at the Technical University of Munich and the Munich Center for Quantum Science and Technology there, but will soon join the faculty at Urbana-Champaign. So I didn't know exactly how much background and context I needed to provide, and so I may have erred on the side of giving you too much, and don't be offended in that case. So I'll sketch the context. I will be very brief about each of these points, obviously. I will touch on some things that are important without giving you a lot of details. And the complete proof of the result is, I mean, it's a not so long paper that we recently revised, but it's based on a previous paper that is more than 100 pages. So in full generality, it's kind of, there's lots of details to be taken care of, but I will explain you what the scheme is, the structure is of the proof. And of course, before I do that, I want to tell you what it exactly is that we are talking about, why we call it the bulk gap. It's a context where we can, if we want to, and if it's interesting, we can ignore edges of the physical system we can talk about, because edges influence the spectrum. And if you want to prove that there's a gap in the bulk, you kind of have to be able to ignore them. And that's what this talk is about. So I will introduce the systems, what we're talking about, how it's formulated, what the bulk gap is, what stability of spectral gaps is, what sort of the general setup is that we use to prove a property like that. And then what the strategy is in this particular situation to do the proof. And then I will compare with some other approaches. We sort of work out, we follow the approach introduced by Bravyi-Hastings-Michalakis, now starting at least a dozen years ago. But there are other approaches, older ones, newer ones, and I will sort of, in some remarks, compare these approaches. And since I'm talking about this one, probably I think it's the best one. I think it is. Okay. So our setup for quantum lattice systems, we're going to do this on what is called a lattice, but in fact, it doesn't have to be a lattice. And sometimes interesting that it's just a discrete metric space with some regularity property. So it's the D is the metric, and it could indeed be a lattice, for instance, Z nu, and then it would be true that the number of points in a ball centered at X of radius R is bounded by some power law, some constant times the radius to the power nu, right? I'm not going to assume it's Z nu, but I'm going to assume that there is such a bound. And for instance, many people work with Delaunay sets because that's, for instance, something you have. It would be, but there are other properties you don't need. That's essential, that it's finite dimensional in this sense. Okay, so then the spin system that I'm talking about, it could also be fermions, by the way, and there is really no fundamental difference. I mean, maybe there's a few details that make it even more interesting, but at the fundamental level, it's pretty much absolutely the same formalism that led for concreteness just talk about spins. So what that means is that the algebra of observables of the system is constructed by taking a matrix algebra and by n matrices, and n may vary from side to side. And then we take the tensor product and for the finite volume observable algebras, and I think with that probably most of you are familiar. These are naturally embedded in each other. If you add sides, if you add tensor factors, you put the identity matrix, and you just get an isomorphic copy of the algebra. So they are embedded in each other in a natural way. You can take the inductive limit. Essentially, you can take the union of all these local ones. You get the local algebra. You can complete it for the standard sup norm, operator norm, and you get a C-star algebra. This is the algebra of quasi-local observables. So I hope this is familiar to everybody. We'll often talk about the support of an observable, and what it is this. So if you have an observable in a lambda, then it would be supported in lambda, the smallest lambda for which you can say this would be the support of A. It could also be an infinite set in principle. Because after taking the completion, I can take limits. The support doesn't have to be a finite set in general. Okay, so this all goes very quickly. And so there is about each of these topics now much more to say, but these are sort of the essentials. So there is this local algebra that you start by constructing, just taking finite tensor products of matrices. And then you complete it to the C-star algebra. So by the fact that we've obtained it by completion, you can approximate these general elements by a sequence of local elements. But it doesn't really. But that's all it says. It says it can be obtained by a convergent Cauchy sequence. It doesn't say how fast the sequence converges. And sometimes you want to know something about that. And that's where you need some way to specify whether perchance some of these observables can be approximated by Cauchy sequences that converge fast as you let these supports increase. So, and the way I'm not going to talk too much about it, but there's different ways of doing it. Take a sequence of finite subsets of your discrete metric space that is increasing, and eventually the union is all of gamma. Fix one, and then you can construct local approximations of your observer by taking conditional expectation. And there's different possibilities, but you have no reason here to take anything but the standard one given by the normalized partial trace, which means that you define a conditional expectation by taking the identity tensor with the tracial state on the complement of the algebra associated with the complement of this finite set formula. But it doesn't even have to be finite, right? So if you have an observable that has a support that is larger than lambda, then in terms of the sort of standard quantum mechanics operations, what you would be doing is taking the partial trace of the stuff that sticks out, you trace it that normalized trace. Each trace at each side is divided by the dimension of the space. So then that's a conditional expectation. The result is something in the algebra of lambda. And then if you have a function, some positive function that decreases to 0, I can use it, or if you want its inverse, to measure how the projections in lambda n of A approximate A, and use that to define a norm. Or at least I define a norm on it when this is finite. So if f is a decreasing exponential function, then the norm thus defined for observable A's would be finite. This object here would be finite if you get an exponentially good approximation by taking these projections on increasing boxes. You choose some lambda n, maybe it's z nu, maybe it's hypercubes. We let the size of the hypercubes increase, and as you do so, for this particular observable, which is norm is finite, you have an approximation that is that converges as fast as f goes to 0. Then you can show that this is a Banach star algebra. It's not these are not C star norms. It's not going to be C star algebra, but you can complete it and so on. It's a nice thing. There's more things to say about it, but I refer you to these papers where this is proof. There's in fact also other approaches, but I will use this kind of notion, and I will I'll usually formulate results for functions that are of stretched exponential decay. You can do other things. You can do power laws or things like that. But maybe I will have time to say why this is sort of a convenient choice for us. Okay. Now then, I want to talk about physical systems for which I have a dynamics, which means Hamiltonians. We define these Hamiltonians in terms of interactions. And in principle, in the reality of physical models, they already all parts of the system interact some way with all other parts of the system. And so sort of a generic way of describing that is by saying that the Hamiltonian associated with some finite volume lambda actually has salvage-on terms for potentially each x in lambda. So this phi of x is a map from the finite subsets of the lattice to the corresponding algebra, ax, right? The salvage-joint, and then I sum all these salvage-joint elements. I get the salvage-joint thing, the Hamiltonian. For physical models given to you, typically this phi is kind of very simple. Maybe it's a nearest neighbor interaction, and most of these terms are 0. The only non-trivial contributions come from x's that are just contain of two sides. It is nearest neighbor, two nearest neighbor sides in, let's say, your integer lattice or something like that. But in fact, at the technical level, to prove what we're going to prove, we need to very much use more general Hamiltonians, where in principle all these terms are non-vanishing. We need to construct the dynamics for those and study properties of that dynamics. And so that's why I set it up here in this general way. So the dynamics is the Heisenberg dynamics. And for finite volume, I can define the unitaries by exponentiating the Hamiltonians, conjugating with the unitary observables in A lambda, defines an automorphism rho T. In fact, it's a nice one-parameter group of automorphisms defining the dynamics in finite volume lambda. You can also consider Hamiltonians that are depend on time. So the interactions themselves could also depend on time. In fact, it's also used in the proofs. I mean, you can kind of ignore it if you don't want to know about the proofs. I won't explain it in detail anyway. But we use dynamics generated by time-dependent interactions. Then you have to solve the differential equation, or do for finite volume, you can do a Dyson series expansion or Diagonal expansion and explicitly construct these objects, but you get cocycles of unitaries that again find automorphisms that give you the dynamics. And now it's parameterized by the initial time and final time. So that is dynamics for these quantum lattice systems. Now, so I constructed the observable algebra for the infinite system, and the properties I want to prove make sort of in the most clear way sense if I talk about infinite systems. And for that, I will have to assume that these interactions, these terms that are associated with larger and larger set x, the phi x's, are more local than just belonging to the C-star algebra. So I'm going to do that again with some kind of decay function. I use it in a slightly different way. Again, there's different ways of doing it. It happens to be my favorite way. I use another function, I call it capital F, to sort of distinguish it from the little f, but it more or less plays the same role. I'm going to assume that it has an additional property, but it only makes sense if you're actually interested in doing the estimates. This kind of convolution property that if I take the product, so I take f distance x z, f distance z y, a sum over z, I get something that's bounded by the function taken in the distance of x and y. So for stretched exponentials multiplied by some power laws, such a property is true. I would in general have to assume that it's uniformly summable. So no matter from which point x I start, I sum over all y. This gives me some constant uniformly bounded from all x. And then I'm going to measure the strength of the interaction by doing the following. I'm going to measuring the strength of the interaction, say between points x and y, by summing all the terms in the Hamiltonian. That is subsets x that contain 2 points, x and y, in the lattice. I take all these interaction terms together. And then again, I have this decaying function. I divide by it. I penalize by this property. I take the soup over all pairs of points. That's a norm. Defines a nice Banach space of interactions. And here again, so in Z nu, maybe I can use these kind of power laws. Power is large enough, it's summable, it satisfies this kind of inequality. I can multiply by a stretched exponential, there will still be an f function. I can also multiply by some other functions, and it will be a nice f function. Just to show that there is plenty of examples. And then I will work with interactions that for one of these f's have a finite norm. In a few places, maybe I'll lose it. Notation bf as the Banach space of all interactions that have a finite f norm for a given f. And then, so let me immediately go to the first thing I want to use this for. So from the moment you have an f for which an interaction has a finite f norm, an f of the form not of the form that satisfies this convolution property and the uniform summability, it's all you need. You will be able to take the thermodynamic limit of these finite volume dynamics, the way I've defined by just conjugating with the unitaries, defined by the finite volume Hamiltonians. So I have fixed t and the fixed and observable a, and I take the limit n to infinity over any sequence of increasing volumes that eventually encompasses the whole lattice. And you can show that that exists in norm in the C-star algebra, and in fact that the limit is independent of the sequences lambda n, sequence lambda n that you have chosen. Okay, as far as dynamics goes, boundary conditions or shapes of volumes play no role if you have a finite f norm. And what you get in the time-independent case, you get a strongly continuous one-parameter group of homomorphisms. That's our dynamics. If the interaction here you can have a time-dependent interaction. Maybe it's defined for times in a finite interval. That's where this notation comes from. But then again, your group property would be replaced by a cocycle, some composition property, and you would have 2 parameters just like you had finite volume. So this is very nice dynamics. It's nice, and there's 2 very nice things about it. So the first thing is strongly continuous. We'll use that in a second. The other thing is that it satisfies the Robinson bound, and you probably have heard about the Robinson bounds. And again, so not to spend too much time on it, it's something that is very useful here in practice to measure how local observables are. And that's sort of the way it's used over and over again in this business. And in particular, what it allows you to show is that if you're going to evolve an observable, so suppose you have one of these interactions with a finite f norm, maybe an f that decays exponentially, and you're going to take a local observable, so one that is strictly local, maybe only 1 side, 2 sides, 3 sides, and you evolve it in time, then that will be not just a quasi-local observable in the C-star algebra, it will actually have this locality where you can use an f that also decays exponentially, meaning that if you take partial traces outside some large balls, say, then as the radius of the ball increases, you have exponentially fast convergence of the approximations. I didn't intend to, say exactly that it was done because many of you most likely have seen this, but that's how lead problems sometimes come in here in this business. How are we going to use them? Now, what are ground states? We're talking about gap ground states. So first, let's talk about ground states. And okay, we don't need this, but I'm mostly going to work with a class of f functions for which I have at least stretched exponential decay with some exponent theta greater than 0. And then, so it so happens that so a strongly continuous group of automorphisms has a generator, and this is the general theory of semigroups tells you there's a densely defined generator, something like this. On the proper domain, you can exponentiate and you get your dynamics back. So I'm not going to go into details of that either. These domains here, you can find dense domains that maybe not are maximum domains, but dense domains very easily if you have this kind of property of the interactions with this kind of F norm. And then, of course, the derivation, what is it? Is the generator of this automorphism. So it's sort of the infinite volume analog of what we'll be taking the commutator with the Hamiltonian. Right? I don't include the I in the definition of generator, so otherwise I have to write I's everywhere. Right? So just commutator with the Hamiltonian. The Hamiltonian is the sum over such terms. Now, if I take a local A, then of course this will be a finite sum, and this is well defined. And you can, in fact, you can show it's a closable operator and so on. This is a well-defined object, and it uniquely determines the dynamics. So you can exponentiate back and solve the differential equation and get the dynamics back. And then a ground state for a given system with a given generator is simply defined as those states, those positive linear functionals on the observable algebra that satisfy this inequality, or A's in the domain of delta, or you can actually, it's sufficient to take A's in some, say, the local observables in this case. This is positive, and one way to look at it is it expresses the fact that perturbations defined by A, for instance, you can define Lindblad semigroups generated with this operator A, and then this will be the derivative of the energy under this Lindblad perturbation. So it says you start doing things to this state, the energy will always go up. Definition of ground state, I'm probably familiar with. They're time invariant states, and that means that I can implement the dynamics in the GNS representation by Hamiltonian. So the GNS representation of our system is a representation of the C-star algebra on some Hilbert space. And it's a cyclic representation, and the cyclic vector represents the state, right? So you can write the expectation of observable A as the vector, the expectation of the vector state omega of the representative of A. So since I'm not going to do proofs, how may not be that important, except that to talk about the bell gap, it's exactly this description in the GNS representation that we want to use, because it allows us to define the infinite volume gap, and it will allow us to prove some kind of perturbation theory for the infinite volume gap. So what I just said is that, so because it's a time invariant state, you can then quite easily show that there is going to be a non-negative self-adjoint operator for which this omega is a ground state, and the Heisenberg dynamics generated by the self-adjoint operator is in fact the representative of the dynamics generated by the automorphism we constructed before. So now we have the Hamiltonian, we have a self-adjoint operator, which has non-negative spectrum, and 0 is the ground state. So that's exactly what we need to be able to talk about ground state gap. And so let's assume, like you often see, and we could discuss it most time what happens if this is not the case, but let's assume that this omega is in fact the unique ground state of this Hamiltonian. Right? This includes cases where the inequality has more ground states, has more solutions at the level of the states on the algebra, but in this particular representation, there's only one state. Right? So let's focus on that situation. So then, what is a gap ground state? Well, it is what you think it should be. It's one for which there is a positive number gamma, such that if you look at the spectrum of the salvage-on operator, H omega, okay, we know it contains 0, but if you intersect with the open interval 0 gamma, you find no spectrum. There's a positive gamma for which this is empty. Right? So there is 0, and then there's nothing in the spectrum up to a certain value, and then of course there will be more spectrum. And this is actually equivalent to this inequality. So a ground state was where the left-hand side here, this expectation was always non-negative. A gap ground state is one for which you have a lower bound for this. If you take an observer with 0 expectation, then it gives a lower bound of the form gamma times omega A star A, and that's gap ground states. So if you can prove this for a certain gamma, then gamma would be the lower bound for a gap in the Hamiltonian. All right, good. The gap itself will be the largest, will be the super gamma, so that you can do that. So, what I want to say now that if I do this for instance, a system defined on the integer lattice, then I claim that this gap would be what is referred to as the Bell gap. But I could sort of restrict my system. I could take gamma to be just a half plane instead of the full two-dimensional square lattice. Then, of course, I could do all of these things. I could consider systems and ground states and things like that and define a Hamiltonian. Whether it may have a gap or not have a gap. But I would be talking about if I do this in such a way that this I have this half space as one fixed half space, so I'm looking at the system from an edge, then it would be the edge spectrum. Spectrum of my GNS Hamiltonian in that case would be the edge spectrum. And so even if you start from a fixed system with unique ground state, but if you restrict it to a half space, the spectrum of the GNS Hamiltonian in general will be different. And the edge spectrum can very easily be gapless, while the bulk spectrum has a gap. I'm interested in the question of stability of the bulk gap, right? So first of all, there has to be one. And so since I'm taking sort of the naive approach that I want to have an operator with a spectrum, I want to study the spectrum, I will have to take the operator that describes the bulk spectrum. I cannot prove the stability of a gap by looking at an operator that doesn't have a gap. Okay. So that's straightforward. So in general, what would I mean by stability? Well, I wrote this here with a lambda, so in principle this could be a finite system. For a finite system, there's always some degree of stability. So I do the following. So I have a Hamiltonian, and then I add a perturbation, another salvage-on operator in general. And I put a small coefficient in front, maybe not so small, that this parameter S is a real number. And then we know, in our case, if lambda is really finite, these are all matrices, it's finite dimensional. And in any case, if I have eigenvalues, they will, as a function of S, be described by continuous curves. So this is a spectrum, so these are the eigenvalues in this particular example. So maybe this is a ground state, maybe this is 0. In this case, maybe it was not simple, it may have been degenerate. Then then I have a gap to the next eigenvalue. You perturb, they in general split up. But since they are continuous curves, for any value of gamma here that is less than the gap, I will find a first value of S, this parameter, when if it ever happens. It could be, this could be infinite, but certainly it's not zero. There's a non-zero value before this gap, this distance here shrinks down to size gamma. Okay, and so I'm interested in the behavior of this S lambda gamma. Stability would mean that I can find a lower bound for this S lambda gamma uniformly in lambda. And I want to talk about the terminal impedance. And so in most cases, that's how it's formulated. You study finite volume gaps, and you show that there is some estimates that you can obtain uniformly in the finite volume. This is the part I'm going to do a little bit differently. Okay, but that would, in general, that's what stability refers to. Is that clear enough? Yeah. Okay. Good. All right. So I'm going to talk to the. So I will repeat here what I said about this gap in GNS Hamiltonian, and will be my bulk gap, right? So I take one of these states, gap ground states with some gamma zero. So I'm going to have a perturbed system, and so the system I'm perturbing supposedly has a gap gamma zero, or at least gamma zero, right, in the GNS Hamiltonian. So then what I'm going to do is add some other Hamiltonian, add another interaction. And so I'm going to simplify. Well, this stability theorem doesn't apply to the full general class of models that I introduced. It will apply to a class, an interesting class of finite range models, so-called frustration-free models. And so the unperturbed model, I'm going to denote the interactions by HX's, and I will be a little bit more specific about that. These are the unperturbed models, and then there is other terms, Vx's, which you can think of as consisting of all the interactions that occur in the neighborhood of some site X. So I'm going to have interactions that are in principle associated with balls centered at X of arbitrary radius, and I'm going to sum all of them up, and then I sort of have this perturbation. And I'm going to assume that these terms that I add decay in a certain way. Some other function G, maybe it's also a stretched expression. I'll repeat these conditions in detail again. And then we want to do stability for that. So now I would really like to show this, what I said before, without any lambda. This is now just the spectrum of the GNS Hamiltonian. But it's not the GNS Hamiltonian. Each GNS Hamiltonian comes in its own representation, right? But nevertheless, I can look at the spectrum for each of them, and I can ask myself, how does this spectrum depend on S? And if I have some gamma smaller than the gap of the unperturbed model, can I perturb or something? I mean, it will depend on gamma. Can I perturb some non-vanishing amount with this perturbation so that the gap at the perturbed model is bounded below by this positive gamma? So this is the analog of what I have here, but without lambda for the infinite system. Yes?
Just to clarify, there is no connection between the GNS Hamiltonians and the representation involving capital omega at different values for the S. Is that correct?
No, a priori there isn't.
Okay.
So what I just said that is obvious here is not obvious in general. So for instance, so I know that in finite volume, definitely I have some kind of stability, maybe depends on lambda. I don't know whether I will have that. But I'll describe an approach where I can nevertheless see something about it. So that's what I want to do. So now, how do we get there? Because yeah, right, a priori, the GNS Hamiltonian at some non-zero value of the perturbation, since it's defined in a different space, it's not immediately clear how to compare it with the unperturbed model. But here's a way to do it. So So I'm going to, so in principle, I'm interested in this kind of system, but I want to go to the infinite volume. And I'll tell you in a second how I'm going to do that. But let me get these conditions over with, because I know you will forget them. So it's better to forget them already. But I mean, they're reasonable and they are essential. So it's not, well, some are essential. I will discuss it in a second. Okay, so I'm going to assume that this unperturbed model here, that's defined by terms that are a finite range. So they are, Hx is always going to be a local element in the algebra associated with the ball centered at x of radius r, some fixed r. Maybe nearest neighbor, maybe it's a radius 10, it doesn't matter. And it's uniformly bounded. We have some gamma as before. And then, so I have to assume something, which fortunately is very satisfied. So I don't know whether these finite volume Hamiltonians that I define. So if I now take lambda to be some large ball, then I don't know that there's a uniform gap for these, because this large ball is a finite volume which has an edge, and if it's a system of intrinsic edge nodes, then these edge nodes will show up. And typically, if energies that become smaller and smaller as the ball increases, and so there is no uniform gap. So I'm not going to assume that it has a gap, but I'm going to assume that as the radius of the ball increases, this gap doesn't vanish faster than some tau. This is generically what you find in interesting systems. So that I have to assume. Now, there's some power law that lower bounds the gap in, say, finite balls. The GNS Hamiltonian, though, of the unperturbed model has a gap. There is a bulk gap of the unperturbed model. That we can prove in certain cases. And then, so this is all reasonable. I will have to assume that this is a little bit stronger than is strictly needed, but I can get explicit things if I assume that these perturbations are not really long range. That is, if as n increases, this decays in norm as a stretched exponential. And then I'm going to assume this condition here, which I call LTQO, which is of course an abbreviation, but it's much easier to say LTQO. And it comes from local topological quantum order, but the name doesn't really explain what it is anyway. So, but it explains a simple idea that is something that is necessary to prove stability of a gap. So it says the following. So if you look at the projection onto the kernel of this Hamiltonian, this is a frustration-free Hamiltonian. I didn't write it here. Again, so these are positive, and we're going to normalize, so then the ground state energy normalized to be 0. And so this is going to be the projection on all the ground states of the unperturbed model. And I'm going to use it for balls. And then I'm going to look at the following things. So I take some A in a ball. So for all x, centered at x, A is in a ball of radius, supported in a ball of radius k. I'm going to project, I put it in between the projections of the ground states in a ball of larger radius m, and compare that to the expectation of A in the ground state times the projector. So there's different ways to rewrite this formula, but if you work this out, so suppose normally, there's no reason to assume, even if the infinite volume system has a unique ground state, the finite volume Hamiltonians may have degenerate ground states, and many of these models, they have many ground states. Think about a toric code model square or something like this. And so this says that the expectation of A is the same in all these ground states essentially, so that this operator just becomes proportional to the ground state projection. And the error decays with the difference between the radii. So if I have my observable here and I look at ground states defined in a larger volume, and as this volume increases, I have convergence. And I'm going to be able to prove what I want to prove. If this error decays fast enough, this function G naught is decaying fast enough so that it has a finite moment. Or actually, it's square root. There's different ways of expressing it. It decays faster than some power that is sufficiently large. That's what I mean. Like, this has to be a finite constant. So I know this is like kind of a mouthful, but so all one-dimensional models with matrix product ground states, parent Hamiltonian will satisfy this. The toric code model will satisfy this. Also, EKT models in higher dimensions satisfy. Some of these properties in LTQO has been proved only in a subset of cases. It's not necessarily easy to prove, but it's certainly believed to be true for these models with unique ground states.
Question about condition C1.
Yes. C1.
Yes.
So, right. So, yeah, I just probably shortened this slide. So the HX's are non-negative. And the assumption is that the ground state of H0, so just these terms is 0, right? And so I'm talking then about the gap of this above 0. And I'm assuming a lower bound of the power law nature.
But my question was, how easy would it be to prove that in practice?
For a general model, I don't know. But for many models, for some models we know it's order 1. For some of these frustration tree models, for others, people think that generically, if you have one of these topologically ordered systems, it should be a specific power law given by whatever the boundary theory is that describes the edge states with a power 1 or something like that. But there's other cases where I can prove it, which maybe not necessarily relevant. But this is not so easy to prove. But in fact, the assumption here is also very hard to prove in general. So we are asking here about stability of a gap, and there's models for which we know that there is a gap and we can prove it. There's many models for which we would like to prove it, but we don't know how. It's not an easy problem. It's not an easy problem.
Could you just quickly explain that the second from the last line is the PAD?
Right. So if suppose let's first suppose there's a unique ground state, then it's clear what this means, right? If this is a rank 1 projection, then this here is going to be the expectation of A times the projection, where the expectation is taken in the vector on which this P projects, which is a finite volume ground state, right? Now here I put the expectation of A in the infinite volume ground state. So I'm saying that this finite volume expectation converges sufficiently fast to the infinite volume expectation. So this C4 we can prove for all one-dimensional systems with matrix product ground states, the finite set of matrix product ground states. Now, if you have more ground states, then it says that all of them should have this property, and in fact converge to the same number. I mean, this can be generalized in the case where there are multiple ground states, discrete symmetry breaking and so on. But I don't want to make it more complicated. So I'm assuming this in this case. So this applies to the situation where we have a unique infinite volume. So it follows from this that there is a unique infinite volume.
But it is a statement that it does involve the infinite volume ground state.
Yes. So right.
Everything else there is finite volume, right?
That's correct. Now, of course, I could also say if you look at this as a function of M, it's a Cauchy sequence, and so on. And I could sort of avoid writing this number if you, but it wouldn't help you very much. Right. But that's right. I mean, you give it's one reason why. So if you have a model with an infinite volume ground state, you know something about it, but it's not particularly simple. You have some prescription how to compute these expectations. It may be sufficiently complicated so that you have a hard time proving this inequality. This is true. So recently, just last year, people proved it for some T model defined on a decorated hexagonal lattice, and it's a non-trivial thing. In one dimension, it turns out for models with a finite number of matrix product density, it's a general simple statement using the transformator. When you go to 2 dimensions, it becomes hard. So, you okay? Yeah, okay. All right. So here's just to have some pictures. So there are systems where what we prove may be the only approach to proving stability of the gap in the bulk so far known. I mean, there are other ways sort of around this problem that in finite volume, whenever you have an edge in the system, you generate sort of edge states that close the gap and make it impossible for you to prove a non-vanishing lower bound. But then very often the topological model, for instance, you can put it on a torus, you do periodic boundary conditions, and you get rid of these edge models. But this is not always possible. And for instance, people like to study these nice, this could be your gamma, this could be a depiction of your gamma. It's a Penrose tiling in this case, but it could be other tilings. It could be a quasi-periodic structure. You can apply periodic boundary conditions to a quasi-periodic structure, obviously, without significantly modifying it. And in fact, if you do calculations, I mean, this is just an illustration. Terry Loring did developed a method to look at edge states in systems like this, and that here he depicts sort of where energy of certain states is localized on finite pieces of lattices like this. And so these are states where the energy is localized about the edge. So there are typical systems where you have edge states and you have this quasi-periodic structure, and you can cut the different shape, but these edge states will follow the edge, and you never get rid of them. Right? If you would know all of its spectral analysis, of course you could say I just add a spectral projection of the constant of all these states, but you don't know them. You don't in general know whether they're well localized or not so well localized near the edge, and so you don't know what to add. So the approach here that we have doesn't need any of that. So here's the theorem. Stability of the bound. So under these conditions, you can in fact prove the following, that there's a constant beta. That's pretty explicit, but the C0 is still there. There's another constant you have to calculate, which depends on all these assumptions that I have made about the decay of the perturbation and so on, and this function that appears in the LTPO condition, so that you're going to have a gap for perturbation parameters as an absolute value less than this number here. So this is the unperturbed gap minus the gamma you want to have as a lower bound. So if you take S less than this number, then the gap of the corresponding GNS Hamiltonian will be bounded below by gamma. So that is the stability property of the GNS, the gaps of the GNS Hamiltonians of these models. And we do modify the strategy that originally was developed by Bravyi-Hastings-Michalakis, started with the code model, and then it was generalized by Michalakis and Zwollak. And so we sort of apply that to this more general situation. I've been going too slow. So I should stop in 5 minutes. When did we actually start after the?
I think we started a little bit late.
Yeah.
So, yeah.
Okay, let's see where we get.
Yeah.
Okay, so what is this strategy? There are some simple general things that go into it, and then there is something that Hastings invented, so-called quasi-adiabatic evolution or spectral flow, and that's what you need. So what are the simple things? So the first thing is that there is a sort of a general level repulsion principle for spectrum of Selbelsson operators. which I'm sure you've seen in matrices, in 2x2 matrix, we can do by explicit calculation. So it is the following: suppose you have self-adjoint operator and you know densely defined, and you have decomposition of your Hilbert space H in K and the orthogonal complement of K is a closed subspace and orthogonal complement. And suppose that the energy of H on K is bounded above by A, and the energies that you find in the orthogonal, the other subspace, the complementary subspace, is bounded below by B. And if A is less than B, so if these energies measured in these states have a gap, so if this is an untrailed interval, then in fact the spectrum of H itself will have a gap. So what does that mean? So let's translate it. So H, of course, it doesn't. These are not invariant subspaces. They're not assumed to be invariant subspaces. So so A is sort of a block operator, if you want, in this decomposition in K and K perp, where S is an operator that goes from K to K perp, right? So what we are saying is that if the spectrum of the A block here is in minus infinity A, and the spectrum of the B block is in B plus infinity, then it doesn't matter what S is. If A is less than B, then this will be a gap in the spectrum. So in other words, adding the S, the only thing it possibly can do is push the A further, the top of this part of the spectrum further down, and the bottom of this part of the spectrum further up. Yeah, this interval is still does not contain any spectrum. It's level of repulsion. So that's a general thing. It's not very difficult to prove. And then the other thing is super easy. So we are going to add perturbations in these extensive systems that, in the end, we are interested in taking to a limit. So this is not bounded perturbation theory, right? It's not analytic perturbation theory. But we can use the concept of relative boundedness, introduced a long time ago by Araki. In fact, we do it in the form sense. So suppose that I call here phi a perturbation, right? And in the end, it will be a sum of many terms, but it doesn't matter. So if you have this kind of inequality, so phi is again not going to be a bounded operator. But suppose that for psi in the domain of the unperturbed operator H, you can estimate the expectation in psi of phi, as the essential part is this here, by the energy in psi. So this is, so if beta was 0, this would say that phi is bounded by alpha, but beta is not 0 in general, in fact, and so it's not bounded by a norm, if you want, defined by H, by the energy. It's a relative bound. And then you can show that, again, if you have a gap, an interval AB, that is a gap in the spectrum of H, then if you start perturbing with phi, so I have H plus phi here, that satisfies this, then this beta will tell you how much the spectrum can move in that interval AB, right? So instead of AB, I will have an interval of the form 1 plus beta A, and 1 minus beta times B, and as there is an alpha, there's also a correction for alpha. That is, if these constants are small enough, I will still have a gap. Right? And then I will apply it, of course, to something, a phi that is of the form S times something, and if I make S small enough, I will have stability of the gap. Okay, in the interest of time, maybe I'll go over the proof. It's super simple, given this level repulsion principle. But I would have to prove relative boundedness of the perturbation. And I didn't really say much about the perturbation. I just said it decays at a certain rate, and some F norm that is finite. And I would really like stability of the gap for all these perturbations. So seems like I'm asking whether all these perturbations, they would always be relatively bounded by the Hamiltonian, the unperturbed Hamiltonian. That's not likely to be true. In general, this will not be true. We'll have to be very lucky. but you can help your luck. That's what Hastings shown, how to help your luck. So what you can, so if these fees satisfy some very specific condition, so this is the same setup I had before. If the perturbations I'm going to use, they annihilate the ground state projection. In other words, it's like they perturb only the excited states. Then you have relative boundedness. So that's good, but the condition is very strong. Right? So then actually you have relative boundedness with a beta that you can compute in terms of these constants. So this is the bound, this is the moment, this is the gap of the finite volume. So that we assume that there's a power law lower bound for this, so this will be convergent if this function g has an efficiently high moment. But do you need this, right? So this would be a very severe restriction of our perturbations. Well, first of all, so this was proved for finite volume, but you can do this in the GNS representation. If what you do is you take the GNS Hamiltonian of the unperturbed system, and then you add your perturbations, you add them in a finite volume only, and you're going to be able to exactly in the same way apply this theorem of Michalakis and Zolak. I mean, some sums are infinite sums instead of finite sums and so on, but it's just a technical modification. But again, it assumes that these fees, these perturbations, they vanish on the ground state space. And that's just not reasonable. It's too restrictive. But suppose that
Unfortunately, we only have the
oh, okay. All right. I'll give you the.
I'm sorry, but we're meeting in 2.5 minutes, the seminar.
No, I'm really sorry, Amish, we're finished. We'll be
Ah,
out in a
okay,
minute,
good.
okay? Yeah.
So suppose I have a unitary transformation. So this is the Hamiltonian I really want to study. But suppose there's a unitary transformation, so it becomes the same Hamiltonian with a different perturbation that satisfies the properties that I need. And of course, I would also be in business because the spectrum, this one, is the same. Maybe there's some offset, it doesn't matter. Right? And so that is what you can do using Hastings quasi-diabatic evolution. Right? And then you apply what I just said after this unitary transformation, and you're done. And so, what is this unitary transformation? This is the unitary generated by the Hastings generator, which is defined by this formula. And you need to do a little bit of work, not to construct it. I mean, it's a time-dependent Hamiltonian. It has some stretched exponential decay. You can study all the properties you need. It will show that it follows the ground states of your perturbed system, and it satisfies the Robinson bounds that you need. And you're going to be able to show that you use the LTKO condition to show that indeed that transformed perturbation satisfies the condition that you need. It vanishes on the ground state projections by applying this unitary. Okay, since time is up, I will just I will stop and you can read the conclusions.
Thank you so much. The probability is right after us, so I think we don't really have time for questions, but I'm going to invite you to come to my office and speak to Bruno if you have questions. So, so you can still ask, just in my office. All right, thank you. Yeah.